Hello and welcome to the session on process synchronization. Before we move forward, here is the learning outcome. At the end of this session, students will be able to uniquely identify the role to ensure the consistency of shared data. What is process synchronization? Process synchronization is the task for coordinating the execution of processes in such a way that no two processes can have access to the same shared data and resources. However, it is specially needed in the multiprocess system when multiple processes are running together and more than one processes try to gain access to the same shared resource or data at the same time. What happens here? This can lead to the inconsistency of shared data. Here, the change made by one process not necessarily reflected when other processes access the same shared data. To avoid such type of inconsistency of data, the processes need to be synchronized with each other. How process synchronization works? Here, for an example shown in this figure, process A changing the data in a memory location means that the process A writing the data in memory location while another process B is trying to read the data from the same location, the same memory location. So here there is a high probability that the data read by second process, that is process B, will be incorrect. So that's why we have to maintain the consistency of the shared data. A cooperating process is one that can affect or be affected by other processes executing in the system. Cooperating processes can be either directly share a logical address space or be allowed to share data only through files or messages. Logical address space means both the code and the data. Here, the former case achieved through the use of threads. The concurrent access to the shared data may result in data inconsistency. However, in this particular session, we will discuss orderly execution of cooperating processes that share a logical address space so that the data consistency is maintained. We know that the processes can execute concurrently or in parallel. The role of process scheduling and how the CPU scheduler switches rapidly between processes to provide concurrent execution. This means that one process may only partially complete execution before another process is scheduled. But in fact, sometimes a process may be interrupted at any point in its instruction stream and the processing core may be assigned to execute instructions of another process. Parallel execution in which two instruction streams execute simultaneously on separate processing cores. Two instruction streams means representing different processes. Here we explore how concurrent or parallel execution can contribute to issues involving the integrity of shared data by several processes. Let us consider an example of how this can be happen. We will discuss here the model of a system consisting of cooperating sequential processes or threads and which are all running asynchronously and possibly sharing data. Here we will illustrate this particular model with the producer-consumer problem, which is a representative of operating systems. Also discuss here how a bounded buffer could be used to enable process to share memory. Now here come to the problem of bounded buffer. As we know that the original solution allowed at most buffer size -1 atoms in the buffer at the same time. Suppose we want to modify the algorithm to remedy this. One possibility is to add an integer variable counter which is initialized to 0. Counter is incremented every time if we add new atom to the buffer, and it is decremented every time if we remove one atom from the buffer. The code for producer process can be modified shown here. The code for consumer process can be modified, it is shown here. The producer and consumer routines shown in the previous slides, which are correct separately, but they may not function correctly when executed concurrently. Suppose that the value of the variable counter is currently 5 and the producer consumer processes concurrently execute the statements counter plus plus and counter minus minus as shown in the previous slide. So following the execution of these two statements, the value of the variable counter may be 4, 5 or 6, isn't it? The only correct result is counter is equal to 5, which is generated correctly if the producer and consumer execute separately. Here we can show that the value of the counter may be incorrect as shown here. Here note that the statement counter plus plus may be implemented in machine language. Register 1 is equal to counter, register 1 is equal to register 1 plus 1, counter is equal to register 1, where register 1 is one of the local CPU register. Similarly, the statement counter minus minus is implemented shown here. Register 2 is equal to counter, register 2 is equal to register 2 plus 1, counter is equal to register 2, where you can see here again the register 2 is one of the local CPU register. Here even though register 1 and register 2 may be the same physical registers, here you have to remember that the contents of this register will be saved and restored by the interrupt handler. So maybe register 1 and register 2 be an accumulator. The concurrent execution of counter plus plus and counter minus minus is equivalent to a sequential execution in which the lower statements presented previously, which are shown here in the interlude arbitrary order as shown here in this slide. Here we will arrive at this incorrect state because we allowed both processes to manipulate the variable counter concurrently. Several processes access and manipulate the same data concurrently, and the outcome of the execution depends on the particular order in which the access takes place, as it is called as race condition. To protect against the race condition, We need to ensure that the only one process at the same time can be manipulating the variable counter. Here pause the video, think and answer. The correct answer is A. Here are my references. Thank you.